Good morning. Welcome to lecture 4. In the last lecture, we briefly discussed converging and diverging lenses. Let's take a look at that again. So if I have a convex lens, this is a convex lens, then I have a set of parallel rays coming in, converge here, and this is called the focal length, which is denoted by F, right? Similarly, if I have a concave lens, then the rays that are coming in are diverging. Sorry. The rays that are coming in are diverging, but it appears as if these rays are coming from a point behind the lens, right? It appears as if they're coming from a point behind the lens, so we would call this as the focal length. So we will discuss a little bit about real and virtual images. So here, in case of a convex lens, the rays are actually converging to this point. So we call this as a real image because the rays are actually converging to this point in reality. Whereas in the case of a concave lens, the rays are really not converging to this point here. They are diverging, and when we are viewing from here, it only appears as if the set of diverging rays are arising from a point source that is behind the lens, right? So that's why we call this as a virtual image. Same is the case with a plane mirror. So if I have a plane mirror, we have seen from Fermat's principle that angle of incidence should be equal to the angle of reflection. So if the ray is going straight, then it is reflected straight back. If a ray is going this way, it is reflected this way. If a ray is going this way, it is reflected this way. So if I am viewing from this side of the mirror, it appears as if these rays are coming from a point source S prime that is behind the mirror. There is no real point source behind the mirror, but it appears as if these rays are coming from an image that's behind the mirror, and we call that as, so that's a virtual image. So we discussed briefly about the focal length. So if you have a lens and you would like to determine the focal length very quickly, one of the ways is to hold it under a ceiling lamp and move it back and forth until you see an image of the ceiling lamp on the floor, and the distance between the lens and the floor would give you a rough estimate of the focal length. Okay. In the last lecture, we have also briefly discussed parabolic mirrors. So here, what we would like to do is we would like to determine the shape of the mirror. We would like to determine the shape of the mirror that we can use to focus a set of parallel incoming rays to a point capital F here, right? So we don't know what the shape of this reflector should be. So we are calling this as S of x. So we would like to determine the shape of a reflector S of x such that this S of x can focus the set of parallel rays to a focal point capital F. So now we will measure all the distances from this dotted line. From Fermat's principle, you know that all the rays should take a path that requires the least time, So if I look at the central ray goes a distance of f this way when it is incident on the reflector, and then it goes straight back because angle of incidence is equal to the angle of reflection. So overall it goes a distance of 2f. Now let's look at the top ray. If I look at the top ray, again we are measuring the distances from this dotted line. While going the incident ray, while going this way, it goes this distance. Now the distance all the way to x-axis is f, and this distance is given by the curve s of x. So this is s. So this distance then is f minus s. So the incident ray travels a distance of f minus s for the top ray. So this is for the central ray. So for the top ray travels a distance of f minus s, after which it strikes the mirror, and then it is reflected along this direction. So this height is x. So this height is also x. This is f minus s, this is x. So this is the hypotenuse, which from Pythagoras theorem should be square root of x squared plus f minus s whole square. This is the total distance traveled by the top ray. Right? So we know the distance. So we also know from Fermat's principle that each ray should take the path that requires the least time. So time is given by distance by velocity. In this case, both rays of light are traveling with the same speed because they are in the same medium. So then we can say that these two rays, the central ray and the top ray, should take the same amount of time. That's Fermat's principle. They are starting from the same point, right? And they're striking the mirror and coming back to the same point. And so they should take the same amount of time. So then 2f by speed of light c, if it is air or vacuum, f minus s plus x squared plus f minus s whole square by c should be equal. That's the time. So this we can cancel out, and then we have 2f is equal to f minus s. We have 2f is equal to f minus s plus x squared plus f minus s whole square. So 1f can be cancelled out. So here we have f. If I move this s this way, I have f plus s is equal to square root of x squared plus f minus s whole square. So if I move the square root this way, then I would have f plus s whole square is equal to x squared plus f minus s whole square, or this implies that I have x squared is equal to f plus s whole square minus f minus s whole square, right? So that would be equal to 4fs, or I can determine s of x as x squared by 4f. So that's a parabolic reflector, right? So that's how we can use Fermat's principle to arrive at the shape of the reflector. So we started with the statement of our problem is I have a set of parallel rays and I would like to converge them to a given focal point f, right, which is at a distance f from my reflector. So I would like to know what should be the shape of my reflector. So I denote that by a symbol s of x, and then I compare the time taken by the central ray and the top ray. They should be equal from Fermat's principle, and just by solving that equation I can arrive at the fact that s of x is equal to x squared by 4f, which is a parabolic reflector, right? Okay, so before we go on further, let's establish some sign conventions. So to establish some sign conventions, we always consider that light travels from left to right when we are discussing lenses and optical elements. So this is, so if you remember this, you can always go back and think about whether a particular sign convention is right or not. So just like how you write, right? We write from left to right. So we are considering light travels from left to right, or at least English, and many other languages. Some languages are written from right to left, but light travels from, we are considering that light travels from left to right. So we would consider radius of curvature is positive if the surface is convex towards the left. So this surface here, it is convex towards the left. So we consider this as a positive curvature, whereas this one, it is convex to the right, so we would consider this as negative curvature. So if I have some optical element or a lens or something like this, then I can complete the circle, right? And this would be my radius of curvature. So a radius of curvature is positive if the surface is convex to the left, and if it is convex to the right, it is negative, right? Similarly, longitudinal distances are positive if pointing to the right. Why are they positive if pointing to the right? Because we are considering that light travels from left to right. So if we are traveling from left to right, any distance that is to the right is positive, right? Any distance that is pointing to the right. So if I have an object here and I would like to measure this distance, this is pointing to the right, so this is positive direction. If I want to measure it this way, that would be a negative direction, right? And any height that is pointing up is positive, anything that is pointing down is negative, and any angle that is this way is positive, and any angle that is this way is negative, right? So even if you forget what these sign conventions are, all that you need to bear in mind is that light travels from, that we are considering that light travels from left to right. Okay. So now let's look at some types of lenses. Types of lenses. Right. So this is a simple spherical lens. So what do you think should be the radius of curvature of this? Is it positive or negative? Think about it. Is it positive or negative? Okay. If you said negative, you need to go back and think about the sign conventions again. So this is convex this way. So this should be radius of curvature should be positive, or radius of curvature is greater than 0. So this is a positive, right? So this is a simple spherical lens, and then we have, oops. So this is a plano convex. So one side is convex, another side is plane, right? So this is a plano convex lens, right? So one side is, unlike a spherical simple spherical lens, on one side we have convex and another side you have a plane, right? So on this side, it is obviously similar to the previous case, so the radius of curvature is positive. So here you have, on the other side you have a plane, right? So what would be the radius of curvature for a plane? It's infinity, right? So on one side, for a plano convex lens, the radius of curvature is positive, and on the other side you have you have infinite radius of curvature. Then what we discussed before is a biconvex lens. Right? This is a biconvex, right? So what is the radius of curvature here? What is the radius of curvature here? I'm sorry about the PowerPoint acting up. The radius of curvature here is 0. How about this side? radius of curvature is less than 0 because it is bulging to the right, right? Okay, now let's look at say plano-concave lens, right? So a plano-concave lens would look something like that. One side it's a plane and another side it's concave. So the plane part, the radius of curvature is infinity. How about the radius of curvature for the concave part? It should be less than 0, right? How about a biconcave lens? So this is a plano-concave. A biconcave, the radius of curvature is, this should it be less than 0? If you hurriedly wrote less than 0 like how I did, you are mistaken. This should be greater than 0, not less than 0, because if you look at it, it is convex towards the left, right? So it should be greater than 0 on the other side, right? But if you did not write r less than 0, that means you're better than me, so you're doing pretty good in the class. Okay, great. So now let's see a little bit more about biconvex and biconcave lenses, or in general we will look at what we call as positive and negative lenses, right? A positive lens creates a real image, right? That means rays actually converge in reality of an object at infinity, or that basically means a set of parallel rays. So for example, one of the examples is a biconvex lens, right? So if I have a biconvex lens, an object at infinity, I'm so sorry about the PowerPoint acting up. Biconvex lens, if I have an object at infinity, then those rays look parallel. So then I would have them converge, right? So they're converging in real time, in reality. So this is the focal length. So this is a positive lens, right? So then you can see what would be a negative lens. A negative lens creates a virtual image of an object at infinity, right? It's opposite, right? So if I have a biconcave lens, right, that would be a negative lens. So a negative lens creates a virtual image of an object at infinity. Again, when I say an object at infinity, that means parallel rays. So if I have a set of parallel rays coming in, this one goes up, this one goes straight, this one goes here. So it appears as if the rays are coming from here. So that's a virtual image, right? So this is a virtual image, right? So excuse me. So a negative lens creates a virtual image of an object at infinity, right? Okay. So if I flip that around, so let's say if I have a convex lens and here I have a point source, right? If I have a convex lens and a point source, the point source is obviously producing rays that are diverging like this. So if I place a convex lens, then I am going to get the opposite case, right? I'm going to get the opposite case. So then I can create a set of parallel rays, right? So similarly, if I have a set of diverging rays falling upon a set of diverging rays falling upon a biconcave lens, then I can convert them rather into parallel rays, right? So we basically are just changing whatever we have looked at before. So a positive lens like this, right, will image a real object at infinity. Right? That means if I have an object at infinity and I'm getting these parallel rays, I can form an image there, right? So a positive lens can image an object at infinity, or if you have a point source, I can create from that diverging rays, I can create a set of parallel rays. And if I have a set of converging rays, and from that set of converging rays, I can create a set of parallel rays using a concave lens, right? So now think about what would happen if I have a set of parallel rays. Think about it. If I have a set of parallel rays coming in, and they go through a convex lens, right? And before they form an image, I have a biconcave lens. Then what would happen before they form an image? Right? Think about it. So we'll stop the lecture here, and we will continue with cylindrical lenses and other lenses, thin lenses and thin lens equation in the next lecture. Thank you.